In the first part of this lecture, we looked at the increase in CO2 in Earth's atmosphere since about the 1960s, which is here, through to the present day, and we're currently up around here at about 415 ppm in 2020. So you can see that's a very steep rise, and we're predicted to go to very high levels in the future. Now, it just so happens that we can create and, well, we can measure records of atmospheric CO2 going back many hundreds of thousands of years. And the way this is done is that scientists, researchers drill cores down into the ice sheets in both Greenland and in Antarctica, and they drill very deep into these ice sheets. And as they go deeper, they get into older and progressively older and older ice, which has been laid down over the years by each year there's more snowfall and it gets compacted and it forms ice, and so the ice sheets steadily build up with time, and as you go deeper you go back in time. And so they drill these big cores into the ice, and here's a slice of a core from an ice core, and you can see it's all full of all of these bubbles. So if you go onto the internet, you should be able to find some high resolution images that show these trapped air bubbles that get trapped between the snowflakes as they compact into the ice. And what scientists do is they extract these air bubbles from the ice simply by melting the ice and extracting the air bubbles. And then they measure how much CO2 and a whole range of other gases that are trapped in the ice to work out how the atmosphere evolved back in time. So here we have this record going back to 800,000 years ago up to the present, which is over here. And the scale changes. So these are hundreds of thousands of years here, and these are hundreds of years here. The last interglacial period, which is about 8,000 years long, is jammed into between here and where we are out here somewhere. And you can see back in time that we have these other periods like the present interglacial period before we started emitting all of this anthropogenic CO2, where the CO2 levels were very similar to what they were in the current interglacial period in these previous periods. And they're separated roughly every 100,000 years, so they get repeated roughly every 100,000 years ago. And they're separated by these glacial periods where atmospheric CO2 levels were significantly lower. So over the last 500,000 years or so, we've seen the interglacials, typical CO2 levels get up around 280 ppm of CO2 in the atmosphere. And then during the glacial periods, they get down to around about 180 ppm, but no lower. And we see this interesting sawtooth pattern of glacial, interglacial periods coming right up to the present interglacial period. And then the other thing that you'll notice is that we've now perturbed the amount of CO2 in the atmosphere through anthropogenic CO2 emissions by burning coal, oil and gas, and also impacts on the terrestrial biosphere have added a lot more CO2 to the atmosphere. And indeed, the other major reservoirs, in particular the ocean, there's additional anthropogenic CO2 dissolved now in the ocean as well, and that's making the ocean more acidic. So the question is, what produces these large variations or oscillations in CO2 and actually ends up creating the glacial-interglacial cycles? Just recalling our observations relating to the measurements of CO2 at Mauna Loa, and you'll remember that at very high latitudes in the Northern Hemisphere, these get much larger, up to 15 or so ppm. So this is 100 ppm. If the growth and the breakdown of leaves on trees with that seasonal cycle each year was to occur, but on a much larger scale, such as the growth and the dieback of forests over tens to hundreds of thousands of year timescales, could that actually explain these variations in CO2 here? So that's a working hypothesis, and we shall do a little bit of critical thinking about that. So, for example, if the forests were much larger during these glacial periods, and we had a lot more forest growth, we could expect that there would be a lot more CO2 consumed, and it would be present in those forests as organic matter in the, not only the leaves, but the trunks and the roots of the trees. And is that growth, is this signal, this oscillating signal, due to expansion and contraction of the terrestrial biosphere? That's the hypothesis that we're going to work with for a second. So let's do a little bit of critical thinking around this. Atmospheric CO2 ranges between this upper limit of 280 ppm and lower limit of 180 ppm across interglacial glacial cycles. So that's the natural variation that we see in carbon dioxide in the atmosphere over the last 1,000,000+ years. And indeed, we haven't seen CO2 levels of the amount that we currently do have in the atmosphere until many, many, many millions of years in the deep past. How much, firstly, let's ask the question, how much carbon does this 100 ppm change in the atmosphere CO2 concentration actually represent? It turns out to be a fairly simple back of the envelope calculation. So we know that there's 600 gigatons of carbon in the atmosphere in the interglacial periods. So the pre-industrial period in the current interglacial had about 600 gigatons of carbon. And we know that the reduction is 100 ppm into the glacial period. So if we take 100 divided by 280 and multiply that by 600 gigatons, we can estimate that during these glacial periods, there was 200 gigatons less carbon in the atmosphere than during the interglacial periods. So the question is, where does that 200 gigatons go? Could that be in the added growth of terrestrial biosphere? So if you remember, the numbers for the terrestrial biosphere were in excess of 2,000 gigatons of carbon in the pre-industrial terrestrial biosphere, and so if that biosphere grew by a couple of 100 gigatons, then we might be able to explain the size of these, the amount of CO2 that's removed during the glacial periods. So I forgot to mention that, how do we know the glacial periods? Well, in the ice core records, we have isotopic information recorded in the ice that also tells us the temperature of the atmosphere at the time. And you can see that the high CO2 levels here in these interglacial periods are associated with high temperatures in Antarctica. So this record is from the Vostok ice core, which is at the South Pole. And so you can see here that the temperature is, and this is actually says temperature anomaly, it's almost 8 to 10 degrees higher in the interglacial periods than what it is in the glacial periods. And that correlates almost 1-for-1 with the CO2 concentration in the atmosphere. So where could this extra amount of carbon actually go in the glacials? Is it going into a larger terrestrial biosphere? Well, if we think about what happens in the glacials, you'll notice that in the last glacial maximum, which occurred around 18 to 20,000 years ago, we know that the ice sheets in the Northern Hemisphere extended over much of North America and here over much of Northern Europe and Asia. And you can compare that to the modern day, where the only ice sheet is in the Northern Hemisphere is over Greenland. And it just so happens that these ice sheets are covering all of the area that's covered by the major boreal forests in the Northern Hemisphere. So actually, we would expect that there's much less forest during the glacial period. So there's reduced capacity to take up carbon, and we expect that the terrestrial, most estimates for the terrestrial biosphere indicate that during glacial periods, there was actually 400 to 700 gigatons less carbon in the terrestrial biosphere during those glacial periods. So this leaves us with a little bit of dilemma if it's not the terrestrial biosphere. So where could this extra 200 plus 400 to 700 gigatons of carbon go during these glacial periods? So that amounts to we've got to find a home for between 600 and 900 gigatons of carbon. So what reservoir do we have that could take up that extra amount of carbon? So we know that the terrestrial biosphere here is smaller by 400 to 700 gigatons, and we also know that the atmosphere is smaller by 200 gigatons. So the logical place looking at this is, the big elephant in the room is the ocean, of course. And given so there's roughly 38,000 gigatons of carbon in the interglacial ocean, we have to find a home for another 600 to 900 gigatons of carbons. So that would only increase the amount of carbon in the ocean by about 2 to 2.5%. So that's not actually a big change. And when you think about it, if the ocean's actually colder during these glacial periods, that might give us we know that when the ocean's colder, it actually takes up more CO2. So you can dissolve more CO2 in the ocean when it's colder than when it's warmer. And the simple analogy there is Coca-Cola, which I'm sure you all know, is that a hot bottle of Coca-Cola, if you release the lid on a hot day, you'll get a lot more CO2 degassing out of it than if you do that with a cold bottle of Coca-Cola. So that's one reason, and it's not the other reason. And we'll come back to some of the other reasons in future weeks in the Blue Planet.